Welcome, everybody. The next talk on the operations track is by Thomas Graf. He is the creator of Cilium and the CTO, I forgot the name, Isovalent, right? I got it right. Okay, so this is about transparent chaos testing with Cilium and BPF. BPF is a really cool technology. I'm already familiar with it on Falco. And this looks very promising, so I hope you enjoy it.
Thank you. So hello, my name is Thomas Graf. Thanks for the intro. Some of you may be wondering why am I speaking about chaos testing. I'm usually talking about networking, BPF, security, and topics like this. This talk is kind of coming out of our own chaos testing that we have been doing. And we figured if we have tooling available that we write ourselves, why not try and use that for chaos testing? So what I'm sharing with you today is how we do some of our chaos testing using the components that are listed on the slide. So Envoy, Cilium, and BPF. Some of you may be wondering how are they kind of connected and how does that lead to chaos testing and what is actually transparent chaos testing. That's what we'll dive into today. So the stack we will build is the following one. We will use what we call Go Extensions for Envoy. If you have never heard about this, we'll do a quick introduction. But in a nutshell, it's the ability to run Go code as part of Envoy. So you can extend and customize Envoy and run Go code instead of writing C++ code. There's several other extension mechanisms as well. We are using Go extension in this case. We'll be using Envoy. We'll do a quick deep dive into that as well. We'll be using Cilium below Envoy as the CNI and networking plugin and as the load balancing plugin. And we will use eBPF as the powerful technology in the kernel that allows us to do a lot of this transparently and efficient. And we'll dive into all of those details, but I wanted to show you the full stack of what we're using up front. So these are the components that we're using to do chaos testing today. So who has been doing chaos testing? Many hands. Great. Who knows what chaos testing is but has never done it? Many more hands. I'm not sure whether that's good or bad. So if you look up the definition, it looks something like this. And it's coming a bit from the original chaos testing talk that came out of Netflix chaos testing monkeys. And it's actually, if you're very specific, it means doing chaos testing in production. I'm not sure if everybody actually has this understanding that it has to be in production. But in a nutshell, it means you're introducing chaos into your infrastructure to better understand failure modes. Right? Now, knowing what chaos testing is, who has been doing unintentional chaos testing? Many hands. That's what I fear. So what we specifically focus on today is called fault injection. And fault injection is one subset of chaos testing. And it basically means that we inject faults into software where a fault is not occurring normally. So the service is actually operating regularly, and we want to inject a fault to simulate an outage or to simulate a service failure and so on. That's what we focus on today. Fault injection is really important as you can test your software how it behaves on faults, and more importantly on combined faults, so multiple components failing at the same time. We'll dig into that in more details. To give you a very simple fault injection example for those that have never heard about fault injection, typically if we simplify it, we have services or microservices talking to each other. And this is a very simple example where one service is doing a REST API call to another service and is making a put to /awesome API func1. And because that service is operating normally, it returns 200 OK. Right? With fault injection, what we want to get to is to this, that we can change what is being returned and, for example, return a 503 application error. Or we would like to delay the response. So, for example, to simulate that the application or the service is taking longer. We may even want to corrupt some of the payload. There's many, many more fault injection strategies. This is a very simple example, but probably the most common, that you simply want to simulate that, like let's say a Go panic in your service code, and you get a 503 because your API handler panicked, recovered, and returned a 503. So this is what we'll focus on. What do we require to kind of do fault injection? First of all, we need a man in the middle. Why is this important? Because we need something in between the services that will change what is being returned. So this is our changing things on the fly. Because we don't want to modify the application to actually return that failure. We want to, on behalf of the application, change the return code. We need the ability to actually simulate a failure. So we need ability to translate or turn a 200 OK into a 504 application error, or a 503, or a 404, or whatever you're testing. We need to be able to delay responses typically, and then the list could go on. Many more things could be needed, but these are the two most common functionalities we need. Then we need a probability aspect. We don't actually want to simulate this failure every single time, right? We want 10% of the requests to actually fail. Because if it's failing all the time, it's probably easier to handle if it's only like with 1% probability that the response is delayed by 500 milliseconds. That's a much harder problem to solve than if all responses are always getting delayed. So we need a probability aspect or a probability multiplier. So yes, inject failure 50% of the times. Then we want transparency. So, and this is maybe a bit new to some of you. We want to be able to do this completely transparent. So you have running applications, unmodified running applications. They're running in production or running in your staging environment. Let's simulate failures in that running environment and see how the applications behave, how your infrastructure behaves. Are the pods restarting? Is auto-scaling working? And so on. It's like load balancing failing over, and so on. All of these things you want to test, and you want to do this transparently. So avoid need to change or restart services. And then the last piece, you need visibility, right? If you have a 50% chance of doing a fault injection, you actually need to know whether that fault injection happened or not, because the service could actually fail for real. So if you get a 503 application error, you want to understand whether this was done by the chaos testing framework or whether the application really crashed or really misbehaved, or whether the delay was done by our testing or whether it was done by the application itself. So was the failure simulated or real? So let's meet those requirements. And this is where we dig into some of the components to figure out what they do specifically. So the first and biggest component we need is Envoy. Envoy is a service and edge proxy. And I think many of you have heard about this either for a while or at this KubeCon. It has understanding of layer 7 protocols. It can also do TCP or L4 mode only, but the primary purpose of Envoy is to act as a proxy and to understand application protocols and then perform various services or functions, such as advanced load balancing, path-based routing, or layer 7 aware routing, canary releases, retries, circuit breaking, rate limits. All of these things, so Envoy as a proxy can perform. It can also provide security services, authorization, mutual TLS, and so on. It can provide observability. This is where a service mesh is I think, very important or is very promising, giving you visibility in all of the API calls, in all of the service communication that is going on, giving you tracing, giving you metrics, and so on. And then Envoy is also extendable. We're looking into Go extensions today, but there's also WebAssembly support coming up. There's Lua. So there's multiple ways to actually extend and customize Envoy and add logic that you need, but is not in the base Envoy distribution. That's a very quick intro into Envoy. If you want to learn more about Envoy, there's many good introductions to Envoy online on YouTube. If you can't find them, ping me. I'm happy to hand them out or give you the links. The next pieces we need is Envoy Go extensions, because we don't actually want to change Envoy C++ code. Envoy does have fault injection built in. What we do is we want to extend that a bit and actually get to the next point. And why this is important is because we want to eventually get to the point that we can no longer, not just simulate a generic service failure, but that we can actually simulate an application-specific service failure. So if, for example, your services are doing some sort of billing transaction, then you want to simulate that the billing transaction failed. You not only want to return like a common 503, you actually want to have the transaction fail, for example. So you want to also be able to do application-specific failure scenarios. And for this, you need the proxy that is parsing the request to understand the actual application payload, like the REST API calls that you make. And this is a perfect use case for Go extensions, because by running Go extensions, we can use the standard HTTP parser of Golang, which gives us the standard HTTP request and response types. And we can bring in all the existing Go-based HTTP handlers, your code, your application code that is written in Go, and run that as part of Envoy and parse the requests and change them and so on. So you can bring in all of the existing Go code that you have, which understands the service-to-service communication. That's the reason why we're running Go extensions on top. Simple Envoy example to kind of illustrate this. So this is an example of using canary releases. So you're running service A, running service B. Service B is currently version 1.0. You could run Envoy in between them, and you could do load balancing. So already splitting 50% of the traffic across both services. You would then want to deploy a new version of service B, and instead of just radically deploying, doing a rolling update, and going and sending all of the traffic to the new version of your service, you would do a so-called canary release, which is something like this, where you start sending 1% of the traffic to service B version 2, and by making sure that all the connections, all the requests from one particular user from one session are all going to version 2, and then slowly ramping up the percentage of the traffic that is going to version 2 of the service. This is a typical example why you use Envoy or what you can use Envoy for. And this is also the mode that we use for our chaos testing later on. Then the next component we need is Cilium. And the reason why we need Cilium specifically is for the transparency aspect, as we will see later. In this case, I will give you a quick intro into what Cilium does and what Cilium stands for. First of all, the unique aspect about Cilium is that it is based on eBPF technology, as we saw in intro. So it's based on, and we'll do a very quick intro on BPF as well, for those that have never heard about it. But it's based on next generation technology called BPF in the kernel, which allows it to be very efficient and transparent and secure. Cilium does a lot of things. It does, first of all, networking. It has its own Cilium CNI plugin, but you can also run it on top of other CNI plugins. So you can also run it on top of something like Flannel or Calico or AWS CNI or Lyft VPC CNI. So we're compatible with other CNIs, and you don't necessarily have to use our CNI plugin. You can also run it on top of others. Then we implement Kubernetes services. We have a full implementation, which is very scalable. It can scale to 10,000s of number of services. We implement network policies, Kubernetes network policies. We also extend them, so we have additional functionalities such as DNS-aware policies, where you can say, I'm reaching out of my cluster. I want to allow all connections to go.com, or I want to allow all connections to star.mycorp.com, and so on. So you can define DNS-based policies. We can do layer 7 aware policies. We can do service name policies, and so on. So we have extended functionality that is not yet in the Kubernetes network policy spec. That is currently in our custom resource definition, and we're working with the SIG network team to get that into the standard and fully supported by other CNI plugins. We do identity-based enforcement. I will not go into all of the details here. That will be too long. But it's definitely a change from IP address or IP-based enforcement into identity-based enforcement. We can do multi-cluster. We can do encryption. We have native Envoy and Istio integration. This is some of what we see today, or in this talk, particularly the Envoy integration. As part of this, that's what we specifically focus on today, is the transparent Envoy injection. So we can get an Envoy proxy in between two services or in front of a service in a completely transparent way without the service to actually know, without the service to even need to run anything inside of the pod. So it's completely transparent to both the service, the pod, and also all other system components. And then a bit more advanced, we can accelerate service mesh or sidecar use cases. If you're running an Istio service mesh or another service mesh, we can accelerate that communication. And in the future, this is not released yet, we'll be able to do transparent SSL visibility. That's kind of the Cilium intro. If you want to learn more about Cilium, just hit me up after the talk. I'm happy to provide more details, whoever is interested. And then the last piece of intro, eBPF, that's kind of the last big component we need. This is super exciting. We're seeing a ton of new eBPF usage in this year. eBPF itself is actually, or BPF itself is pretty old, but most recently we kind of, the need for what we call a virtual machine that allows to program the kernel has become very obvious, and there's been a ton of effort that has gone into this. So what is this eBPF thing? In a nutshell, it's actually very simple. It means that you can run a piece of logic, a piece of code, on certain events inside a kernel. And I've put a couple of examples on the slide here. For example, you can run a BPF program whenever you send or receive packets from a network device. This is what Cilium does on the networking side. You can run a BPF program whenever a system call is being made, like read or connect. This is how seccomp works, right? This is how some of the container runtime protection mechanisms based on BPF work. You can run it on block I/O, right? This is some of how the tracing and metrics work. They actually look at every time your system writes into a block I/O device, it runs a small program and captures some samples. And you can run it for so-called trace points. For example, every time the kernel does a TCP retransmission, every time that event happens, we can run a program. So it's really making our Linux kernel programmable without requiring to change it. And it's done so in a completely secure and efficient manner, which makes this perfect. So we can load a program, it runs at native execution speed, it is secure. So it's basically perfect role. We can extend and customize our Linux kernel and like add more functionality without ever having to change it or without having to restart it and so on. This is why so many people are super excited about what BPF will bring in the coming years. So what exactly is transparent chaos testing? And we'll go through an example to make this clear and kind of put the whole stack that we introduced and put it together. So simple example, service A talking to service B. They're both on 2 different nodes. They could also be in the same node, but let's assume they're on 2 different nodes. It's doing an HTTP request. It will talk to each other, and the first thing that you will need in this case is you need a CNI plugin. I've chosen Cilium in this case, could be any other CNI plugin as well. The CNI plugin will assure that one pod on one node can talk to another pod on another node. That's pretty much the purpose of a CNI plugin. That doesn't give us any injection. There is no Envoy yet, nothing. Pods can talk. Now we're introducing Envoy, and we want to run Envoy in the middle because Envoy will do the fault injection for us. And I've simplified the Envoy architecture a lot, but to keep it very simple, Envoy knows about listeners. Those are ports where Envoy listens for connections. It will accept those connections. It will read on those connections, and it will then pass both the data and the HTTP requests through a filter chain where we can do filtering. And after the filtering has happened, it will go through the proxy layer where it will basically decide where do I have to send this, right? It will decide how to forward this, and so on. And then on top of that, we're running the Go extensions. So the Go extensions are a filter of Envoy that allow us to load Go code up here while keeping Envoy running. And every time that the connection is receiving data, that data will go to the Go extension, and our Go extension can do something with that data. And as we'll see, we'll do fault injection with that. The reason why this is called transparent injection is because this Envoy injection here, the running Envoy in the middle, we'll see in the demo, this happens without the user or without anybody actually noticing. Cilium will bring up Envoy, run it, and then using BPF, magically, it's networking, but it will look like it's magically redirecting all traffic subject to our fault injection policy to go through Envoy, go through the Go extension, and perform whatever fault injection we need. So that's when I talk about transparency and transparent chaos testing, it means that you can have existing pods running, and we can then go and do fault injection and get Envoy into the middle. So without doing actual sidecar injection or without running something anywhere, we can simply instruct Cilium to do transparent chaos testing. Yes, so this is a simple example of kind of how the configuration looks like. So there the Go extension runs, and I will go through this example very simply. This is the Cilium custom resource definition for a network policy. And you will see a couple of things here. You will see that we have a endpoint selector. This is basically the pod label selector, and we'll select what are the pods where this fault injection policy should apply. And in this case, it's all pods with the label app my service. So all of them will be subject to the fault injection. Then we will define that this is ingress. This is a bit of a network-specific term, but it means this fault injection will be done when the request is going into the service. So not when a request is leaving the service, but when it's getting into the service. Then we're basically specifying that every time the service is receiving a request on port 8000, TCP, then run the Go extension chaos. And this is where the Go extension is coming in. And then we're defining with a probability of 50%, rewrite the status code into 504 application error. And this custom resource is all you need to load into your cluster to basically enable this and get transparent fault injection. So let's recap kind of the requirements we saw and how we solved them. So woman in the middle is Envoy, quite simply. Ability to simulate fault injection and probability aspect, that's a Go extension. Chaos. Transparency, kind of loading it on demand for existing pods, that's Cilium plus eBPF. Visibility, HTTP headers and Envoy. We will see the HTTP headers in the demo, what I mean specifically by that. And yes, let's go and dig in, because I've been talking for a long while, and I think we should just demo this. I think it will make a lot of things a lot clearer. So let's move over to the demo. And I have a very simple cluster. And we're doing all our demos Star Wars themed. So in this case, yes, again, it's just Death Star for those who have seen Cilium demos before, and a Millennium Falcon. So this is actually just Minikube, so a very simple cluster. The only thing I deployed here on top is Cilium. So you see the Cilium pod running as a daemon set. This is a one-node Minikube, so there's not much there. But that's the only thing we deployed on top of Minikube. Otherwise, this is a standard Minikube. So I can go on and I can run curl to the Death Star. And this is actually just, as you will see, this is just HTTP bin. So it will return some HTML. I can, for example, curl to headers, and headers/headers will return what are the headers we provided in the request. I can run curl with -i. So the curl will tell me what are the HTTP headers that were returned and the HTTP code. So far, no fault injection. This service is returning 200, okay? You can see this here. Is the font big enough? Or should I? Good, awesome. So there's no fault injection going on. Everything is working perfectly. So how can we do what we just talked about, which is fault injection? So we can look at, I'm actually in the wrong repository, it's good. I want to be here. So this repo is public, so you can try all of this yourself afterwards. I have two simple examples here. Let's look at the first one. So this first one is very similar to what we saw on the slide. It's a policy that says, rewrite the status and rewrite it to 504 application error. Let's actually increase the probability a bit, so we are more likely to hit it. So this is the chaos policy, basically. Let's save it, and let's apply it. Like, very simple. My F key is stuck, that's good. There you go. All right, so I applied this policy. That's all I did. Let's rerun curl. So we just got lucky on the first hit. It actually rewrote the application or the status code to 504 application error. We didn't change the application at all, but all of a sudden it looks like the application is failing. So let's run it a couple of more times. Hit it again, hit it again. Let's see, when are we unlucky? So far, it's always hitting the 80%. No, it didn't hit it. So we're implementing that probability aspect. We can easily change that because, oh, this is actually too much of a failure. Let's change it. Let's look at the YAML. Let's change it to 10%. Let's apply it. All right, and let's run it again. In this case, it should actually pretty much always return 200, and it does. All right. What else can we do? So we can delete the policy. In this case, I'm just deleting all of them because I only have one loaded. I can run it again. In this case, it will always return 200 OK again. So I can inject this, take it out again. It's completely transparent, and your pods don't even know that this is happening. It's completely done from the outside. Let's look at the other one. That's also an interesting one, which is delay response. So if the policy matches, delay the response. You can also delay the request if you want to. In this case, we're delaying the response. So the service has already responded, but we will hold it up. So let's hold it up for, let's make it a bit more obvious. 2 seconds, and let's actually always hit it. So I added it, well, maybe that's a bit quick. So I changed it to 1.0, 100% probability, 2-second delay on the response side. Let's apply that, delay response. Let's do this again, and you can see it should block roughly 2 seconds. It will wait two seconds. And if you delete it, it's instant again. So we can do delay, we can do rewrite status, and so on. We can do many more things. So quick demo, like how simple this is from a usability perspective. What's even more important in this case is that this is all Go code. So if you need additional functionality, it's absolutely trivial to extend this and write whatever additional logic you need because it's all Golang HTTP parsing code, like almost everybody. It's not like BPF low-level code. It's not C++. It's absolutely trivial to extend this. If you want to get started and basically repeat what I just did, very simple as well. I put all of the examples into a Git repo, so you can Git clone that. You can create a Kubernetes cluster. You can use your existing one. In this case, I'm just using Minikube. Very simple. You install Cilium. One command and Cilium is installed. That's just the daemon set. This is part of the chaos testing examples repo, but you can also follow the standard Cilium installation path. You deploy your app. In this case, it's a Death Star and the Falcon. And then you apply the fault injection policy. And that's all you need to do. So very simple. You can try this out using your existing apps. You can use this for development purposes on Minikube. You can run this in your staging clusters. You can run this in your prod clusters if you want, and so on. To go into some more examples, you can combine the probabilities. So you can, for example, have a policy that says with a probability of 80% delay by 50 milliseconds, and then with an additional probability of 20% delay for 1 second. So it's not just one rule, or like you can actually combine them, which is kind of a bit of a more realistic example because you can create the distribution that you are more likely to see. You can also rewrite or match on path, method, on the status code. So you can basically say, only rewrite the HTTP response if the request was a get to /foo. So you can become very specific on which responses you want to where you want to inject faults. So you can not only just match on the pod labels you're matching on or the selected services, you can also apply filters on what are the requests that you want to inject failures into. And obviously, you can load as many of these policies as you want. No, I've only loaded one. You can load as many as you want, of course. With that, I'm happy to take questions before we get to that. All of this is open source. Cilium is open source. The link to the GitHub is there. The link to the examples of all the chaos testing scripts and policies are up there. We have a Slack channel. So if you want to try this, you run into issues, come to our Slack channel. Feel free to ask questions. We're happy to help. And we also have a Twitter account if you want to follow updates around Cilium. With that, happy to take questions.
Thank you for the talk. That was very interesting. Can you tell me, in the delay method, where is the packet being delayed? Is it possible to have a backlog build up if you delay too long on the response side, for instance?
I didn't get the second part. Can you repeat the second part of the question?
If you just explain where it's delayed, you'd cover that. So my concern would be, if you delay a response, does that mean that in the kernel or in the responding service there's a backlog building up?
So the delay is caused, the packet, the request is currently in Envoy, and the response has been parsed, but it's basically held in there. So the Envoy is maintaining a connection to both services, and the response is it's exactly the same as if you do Envoy rate limiting. It's holding the request. It's not actually holding packets, like network packets. It's parsing the full response, holding that for like 1 second, and then sending it back.
Can I do the same with gRPC services in the backend? So is this independent from the actual protocol using, or?
So what the demo I did, I wrote this chaos testing plugin like one day, and I'm using Golang Net HTTP, so it will support any version of HTTP. But the Go extension plugin is on data level, and the plugin I'm using is done in a way that you can now hook in any parser you have that's using the Golang I/O reader interface. You can just plug it in. So you can parse whatever protocol, even if your proprietary protocols, you can all plug it in. The demo I did was HTTP specific.
So where does your Cilium network plugin like stop, and when does your Go extension start? How much work is done in the Go extension? Because Cilium seems to be doing some work under the hood as well.
Yeah. OK, so the Envoy is actually not running at all until we injected the first network policy. So when we did the first apply with the policy, Envoy was started. And at that point, the filter, like, let's go back to the policy. So only the connections that are matching this selector here, so all connections to that's only those will go through Envoy. And then when you unload this policy, no connections will go through Envoy again. So only when needed does it go through Envoy. And then I think you also had a question about overhead. On top of pure Envoy, Go extension add about 10% of overhead just from context switching and so on. Okay.
Maybe the question is going in the same direction because you are using the Cilium network policy, which is special to Cilium and provides the Istio the Envoy integration. Yes. What would happen if I would have a network policy and I would add an additional Cilium network policy for the chaos testing?
Yes, it will respect both. So all Kubernetes network policy and all network policy are so-called whitelisting. So there's no deny or reject in Kubernetes policy, so you cannot even have a conflict, but both will be respected. The only reason why we need Cilium network policy is because there is this part here. This is just a Golang map and allows us to parse arbitrary key value pairs into the Go extension. So you can basically pass whatever configuration you need for your Go extension. That's why I use Cilium network policy. All right, so this is a generic Golang map key value. So as you add more capability, you can just make it configurable. Was another question? Yeah?
Along the same lines, but going towards service mesh, because Cilium integrates with Istio.
Yes.
How will this collide with that, or it'll go through multiple Envoy proxies? How does that work?
You can run this with Istio. All you have to do is the Go extension is an Envoy filter. Envoy or Istio has its own kind of not fork, but version of Envoy. Just add our patch to add our filter, because the Istio proxy does not have the Go extension filter in. But as soon as you add that, and the Istio sidecar proxy becomes capable of running Go extensions, this will just work in the pilot managed sidecar as well. This is the Go extension patch on top is very small, so it's a couple of hundred lines. It's not something massive.
As you mentioned, that 10% overhead for the Go extension, does this also apply if you're writing extensions in C++? Or would that be then almost native performance from the extension point?
The overhead is coming because Go is doing memory a bit different, and there's every time you switch context, it's not really a context switch, it's not kernel user space, but there's a memory context switch between C++ and Go. That's this 10%. But that's not per packet or anything like this. It's every time, it's usually one call per request, and then you get the data for the entire HTTP request, unless it's really, really, really large. What we measured in the worst case is about 10%. It might actually be less. But it's coming, that 10% is because of switching between C++ and Go.
OK, so if we would write this in C++?
Yeah, for sure, yes. Cool. So Go extension is primarily for simplicity. I wrote this like less than a day, which was that's the appealing part of this. Are there more questions?
Could you just describe again how Cilium starts Envoy? Does it key off of that L7 proto in the network policy that you apply?
Yes. So as soon as you have this, so up to this point, up to protocol, it's basically a layer 4 policy, and there's no Envoy. As soon as you have L7 proto and you choose what layer 7 protocol you are using, so we're supporting Cassandra, Kafka, Memcached. As soon as you select one, and that one is implemented by Envoy, which is everything except Kafka and DNS right now, then it will automatically start Envoy.
I think no more questions, so.
Awesome, thanks.
Thank
you.